for coming. Today I will be presenting a paper titled Machine Learning Adjusting Automatically for Human Biases in Decision Making. So what this paper is about risks associated with algorithmic decision making. That is, risks associated with using algorithms to facilitate decision making processes. So this is a very timely project because now algorithms are being used more and more to automatize all sorts of decisions. So decisions with the judicial system about whether, say, to grant parole to an inmate, whether to grant a bail to someone who has been accused of a crime. Inside the education system, decisions regarding student assignment to schools, decisions about assignment of charter schools. In the context of finance and banking, evaluation of customer credit rating. So in all sort of areas, okay, of the social sciences, we're seeing that both within governments and within organizations, companies, etc., algorithms are being used more and more to sort of make all sorts of decisions instead of human beings, okay? Or to help human beings make decisions. So what I'm going to be focusing on is on situations where, well, what can happen if when you estimate your model, okay, so when you train your algorithm using data, what can happen if those data that you use display biases? Meaning, suppose that the data that you use involves decisions that were made by these human beings in the past. Okay? So you see past cases, you say what decisions were made, and now you want to train an algorithm to sort of replicate that same human behavior that occurred in the past. Okay? So what will happen is that if in the past the humans who made the decision behaved in a discriminatory manner, then if you train the algorithm using that data, then the algorithm will basically learn to discriminate. So I'm mostly going to be focusing on data-related problems. But at the very beginning, I'm going to talk about the issue a little bit more generally. Okay, so I was kind of lucky when I started working on this project because a lot of discussion has been going on in the news and social media lately about this sort of problem. Okay, so in January of this year, for instance, Representative Ocasio-Cortez, she participated in an event where she said the following. She said, algorithms are made about human beings, are made by human beings, and those algorithms are pegged to basic human assumptions. If you don't fix the bias, then you are automating the bias. Okay, so she was talking about some of the risks of the type of technological change that I was talking about before. And right away there was this reaction in social media from people saying, oh, well, she cannot possibly be right because if computers are making these decisions, then how it is possible that computers are discriminating in the ways that humans do. And so this example, I like it because it helps justify the need for the sort of paper that I'm writing, which is mostly about sort of clarifying misunderstandings. So yes, if the data that you use for training purposes displays biases, the algorithm will replicate the biases, okay? Unless you take measures to make sure that doesn't happen, okay? And then also something else I want to do is to talk a little bit about potential solutions. Some of the conventional solutions that are used to deal with this problem, okay? Some that are prescribed by the law, are not really good solutions. They are naive. Other solutions that you could think about might end up doing more harm than good. Okay? So I also want to spend some time talking about, well, what is it that computer scientists are recommending these days? What type of solution, what else could you do that maybe would do a better job at taking care of this problem? Okay? Okay, so something else is that in response to this incident that I mentioned, there was some counter-reaction on Twitter of people sort of backing what Representative Ocasio-Cortez say and explaining why it is that what she said might happen. So in particular, I like this response from someone who works on using artificial intelligence for image recognition, who gave kind of plenty of examples of how that can happen. So it's been very interesting sort of following this discussion that's been happening in life. So in order to get a sense, so when it comes to implementation of algorithms, bias in the sense of unequal treatment of different groups might emerge for many reasons and at different steps in the development and implementation of an algorithm. So to get a sense of how that can happen, it's useful to first understand, well, what is an algorithm? So a very generic definition that is sometimes given is that algorithms are just procedures that are used to sort of facilitate decision-making processes and generate advice for decision makers. So this definition is kind of vague because it doesn't really let us get a sense of where it is that biases may emerge. So let me give you a little bit of a more precise definition. In part, I tell you this because I want to just emphasize that I focus on only one particular type of problem pertaining to biases, but biases may also emerge at the other stages, and that's not something that I'm going to be talking about here in this talk. Okay, so an algorithm is an abstract mathematical formulation that is implemented using computer software, typically. So sometimes someone takes a mathematical expression and then writes down code that will behave consistently with the prescriptions of given by that formula. And this computer software is implemented on data sets. Okay? And then the output generated by the algorithm is interpreted by an analyst or a decision maker. Okay? So biases might re-emerge at any stage in the process, from the formulation of the abstract formulation of the algorithm, the programming of the algorithm, the parameterization of the algorithm when someone uses a certain say, computer package with source code that can be used to implement the algorithm. If you have to pick parameters, then in picking those parameters, you might unintentionally end up treating some groups of observations differently than others. Okay? Biases could have to do with issues or problems with the data set, with the data, that's what I'm going to be talking about today. And lastly, of course, when the analyst or decision maker takes and looks at the output from the algorithm, that information can be interpreted in a subjective manner and in a biased manner, where certain groups end up being treated unequally, okay? Different groups. Okay, so again, I'm going to be focusing on the data aspect of this problem. Okay? So when it comes to data problems and all the discussion that has been going on, I believe that there are two sort of big families of problems that people have been focusing on. And just to avoid misunderstanding, I want to very briefly characterize the two types of problems and then tell you which one is the one that I'm going to be talking about today. So one big class of problem, which is not the one that is going to be the subject of this talk, has to do with problems when your data doesn't have enough coverage or doesn't proportionally represent every group in the target population. Say. It could also happen that for some groups you have a limited amount of information. Maybe the sample size for some groups is too small. So when you have lack of coverage, okay, and then you estimate your model using data from some groups only, then whatever recommendation is generated might be ideal for the groups or for the types of individuals that were included in the data set, but might not be ideal for those who are not included. Okay? When you have lack of representation, you might have similar problems, and you also have the problem of the types of people of certain group who are included in the data set might be systematically different from people of that group that were not included in the data set. So you might have sample selection. Okay? If you have an insufficient number of observations from certain groups, estimates for those groups might be very imprecise. Okay? So all of these things might lead to unfair treatment of certain groups. One example that I like, because it has also been in the news recently as a sort of illustration of this sort of problem, is are standards that have been used so far to set the office temperature. Okay, so these standards have been set based on resting metabolic rates seen in men. Okay? So when the standard is chosen in that manner, then men feel comfortable and women tend to feel cold. So that's an example of lack of coverage. Okay? So you're estimating a quantity using data from one group only and not taking other groups into account. Okay? So this is, of course, a very important problem. Okay? But it's also not, for social scientists, it's also not a new problem. Okay, so people who work with survey data, for example, for them, these are sort of day-to-day problems. Okay, so if you have lack of coverage, that's kind of very hard to deal with. If you have some representation of certain groups, then you can deal with this problem to some extent using weights. Under some assumptions, if there is sample selection, you can also make adjustments to take that into account. But again, this is not new, and again, it's not the subject of this talk. I'm going to be focusing on another data-related problem, which is the problem that I was describing before, which is a problem where the training data set that you use displayed unequal treatment of different groups. Okay, some groups were treated unfairly. Okay, so and in all cases I'm going to be talking about decisions, okay, that were made in the past by human beings, and about algorithms are now trying to sort of automatically make the same sort of decisions. Okay, so I'm going to focus on situations where the past treatment of different groups was kind of unfair, okay, towards some of the groups. So these biases that I'm going to be talking about can be generated can be generated completely in an unintentional manner, okay? Because the process through which some machine learning algorithms generate decision-making rules can be highly complex. Okay? So the person who wrote the algorithm or who programmed the algorithm might have been unable, okay, or not aware at all at the very beginning that the algorithm would end up behaving in a certain way toward some groups. So many times we don't see these biases until exposed, okay, until all of these algorithms have been implemented. So many times these algorithms end up generating bias, okay? And bias that maybe was not foreseen from the very beginning by the person who wrote the algorithm. So one example of this happening in real life is the example of an Amazon artificial intelligence algorithm that was used for some time to make hiring decisions, where people whose CVs contain the word women or who attended all women colleges ended up being less likely to be hired. Okay? And so women ended up being at a disadvantage from the point of view of decisions made by this algorithm. And when Amazon realized that was happening, they just stopped using this algorithm for hiring purposes. Okay? And so again, I'm going to be focusing on situations where algorithms, but I'm going to be focusing on situations where you have a data set that displays some biases, and we want to see what can we do to still use that data, but make sure that the algorithm doesn't learn to replicate the same bias. Okay, so let me give you, I'm going to give you both a few definitions of some important concepts, and also to introduce some notation that I'm going to use later in the presentation, and that's going to sort of facilitate communicating some of the concepts. Okay. So first of all, it's important to distinguish between disparate treatment, okay, and disparate impact of different groups, or of decisions on different groups. Because so disparate treatment happens when suppose that there are some protected groups, meaning groups where they are defined by some attribute that legally, okay, we think it shouldn't be taken into account in the decision-making process. So this could be gender of an individual, race of an individual, religion of an individual, and so on. Okay? So when that information is explicitly used, okay, it's seen, it's used, and leads to unfair treatment of certain groups, then we say that there was disparate treatment. Okay? So different groups of people were treated differently based on their characteristics. Okay? So I'm going to be focusing mainly on a different type of problem, which happens when there is disparate impact. Okay, so so there is this protected characteristic or this protected attribute, but it's not explicitly used in the decision-making process. Nonetheless, the decision maker is taking into account information on other attributes that correlate with the protected characteristic. Okay? Whenever that happens, say if that other attribute, okay, is predictive of decisions made in the past, then that attribute that correlates with the protected characteristic is going to, say, influence the decisions that are made in the future, and it's going to lead to disparate treatment of different groups. So there's going to be what we call disparate impact. Okay? So again, in the case of disparate impact, there is an unintentional bias that occurs even when you don't explicitly take into account information on the protected attribute. And it's different from disparate treatment, which is defined when you intentionally discriminate based on a certain characteristic. So one thing that also I'm not going to be doing much in this presentation. So what I'm going to be doing is mainly, well, if there is disparate impact, okay, if we see it in the data, what can we do to adjust for that? Okay, to make sure that the decisions we made in the future don't display a similar amount of disparate impact. So I'm not going to talk so much about, say, normative questions, such as what amount of disparate impact is acceptable, if any. Well, that's going to depend on the context, on the area. It's different if we're talking about a company that is making hiring decisions, that is taking into account whether people have certain training that is necessary to carry out a certain job that will affect the company's productivity. That's different from we talking about the judicial system and whether an inmate should be granted parole. Okay? So the amount of disparate impact that might be acceptable in the different cases depends on the area, okay, on the setting, on the context. So, but here I want to introduce one 80% rule that is kind of a rule of thumb that has been used to evaluate whether disparate impact occurs. And I'm going to introduce it using the notation used in Feldman et al. Okay, from 2014. So suppose that we have a data set D. Okay, so this data set D contains a column, okay, which is with information about the protected attribute, okay, the protected characteristic of the observations in the data set. So Y are other predictors included in the data set, which may be correlated to some extent with X. Okay? So for example, if you're thinking about hiring decisions, X could be, say, the gender of the individual, Y could be training, other education, other information of the applicant, and that information could correlate with X. Good or not? And then C is a column containing the decision, what decision was made. Okay? So we train the algorithm in a data set that includes all the information. Okay? Information about X, Y, and Z. Okay? And here's, just to make things simple, we're going to be talking about an X that is binary, okay? Say male or female, and we're also going to be talking about a binary class outcome. Okay? Was the person hired or not hired? If the person wrote a letter, was a response given or not given? Was parole granted or not granted? Okay, so we're going to talk about yes/no decisions. So the 80% rule, what it says is that there is disparate impact. Okay, if the probability of a favorable outcome, given that the observation displays the protected attribute, okay, divided by the probability of a favorable outcome if the observation does not display the protected attribute, if that ratio is lower than 0.8. Okay? And so the reason why this was useful it was useful to sort of reference this rule in that paper is because then the authors of this paper, they show that whenever this happens, okay, whenever the ratio of probabilities is lower than 0.8, then it also happens that the predicted attribute X leaked into the other information in the data set. What does that mean? It means that in situations where this ratio of probabilities is lower than 0.8, it can happen that you can predict the protected characteristic pretty accurately based on other information contained in the data set. Okay? Okay. And that's going to be useful because you're going to see that then one solution to this problem that I'm going to be talking about involves adjusting the other information contained in the data set such that you remove the correlation with the protected attribute. So then the protected attribute will no longer leak into the rest of the information in the data set. Okay. So let me give you a synthetic example. So this synthetic example is kind of entirely hypothetical, and the setting is also very unrealistic and simplistic. Okay, so the only reason why I'm using such a simple and hypothetical example is because it makes it easier for me to sort of explain what the problem is and what the different solutions are, why some solutions are good, why others are not so good, and also kind of what the consequences of some of these adjustments are. Okay, you're going to see that there is some trade-off. There are some trade-offs involved in trying to make decisions more fair. Okay, and so I feel as if it's using an example like the one I'm going to give you, it's kind of very easy to illustrate all of these things. And also, by using an example that is kind of unrealistic, I also make sure that you don't think too much about the substance, but you think more about the technical problem. And so let's focus on that. Okay? So suppose that legislators receive letters from constituents, and that they receive thousands of letters to a point where it becomes very costly to read all the letters, make decisions about whether to answer every letter, and so on. Okay, so suppose that you have the office of a legislator who decided to automatize the decision-making process, okay, by looking at letters received in the past or information on letters received in the past, seeing whether the letters were answered or not, learning about the relationship between characteristics of past letters and what was done before, and then based on that information, okay, make decisions about what to do in the future with letters where you only see what the letter is about, but you haven't yet made a decision whether to answer or not. Okay? So you're going to basically use an algorithm, a classifier, to automatize the decision as to whether to answer the letters or not. Okay? Okay. So let us make the following assumptions about the information contained in the dataset. Okay, so the information contained in the dataset involves decisions made by staff, by the legislature staff in the past on letters, where they have a data set that tells you for each letter what the writer's position was on 5 issues, including a women's issue. Okay, so this could be positions on contraception, for instance. And let us suppose that women are more supportive of the policy than men. Okay, so in this example, like generated a synthetic data set such that there's a broad gap in positions between genders. Okay, and then you also have information on on the person's, whether the writer shares the same party identification with the legislator or not. Okay? So so then what I did is, based on all of that information, I generated a rating. Okay? And I made the assumption that, so that rating captures the legislator's preference for answering a certain letter. Okay? So the higher the rating, the more the legislator's office would like to answer the letter. And I also assume that there is a threshold above which the office answers and below which they don't. Okay? And I set that threshold at 6. Okay? So the rating ranges from 1 to 10, and letters with a rating larger than 6 receive responses. Okay? So in generating the rating, I assume that the letters with favorable positions on issues 1 through 4 get higher ratings. Letters with supportive positions on the women's issue get lower ratings. Letters from women get lower ratings, even holding constant the women's issue. Okay? So gender, I'm making the assumption that gender was taken into account in the past. Okay? And that women were less likely to receive a response. And then the rating also increases when the letter writer and the legislator share the same party identification. Okay. So my expectations are very obvious and straightforward. Okay. So if you take that data set and you use it to make decisions on future letters. So on future letters, you might say, oh, but then you will have to read all the letters and see what the letters are about and what the positions on the issues are. Well, let us assume that there is some sort of text analysis algorithm that you could use to automatically code for every letter what the positions are on issues 1 through 5, which could totally be the case. Okay? So suppose that for the future letters, you automatically assign them positions on the different issues. So you have the same information on X and Y as for the past letters. You just haven't yet made a decision on whether to answer or not. Okay? So my expectation is that if gender is taken into account, then the algorithm will just treat women in the same way as human beings did before. The algorithm is going to discriminate against women. Okay? Now, if you don't take gender into account, but you take into account information that is highly correlated with gender, then the algorithm will still discriminate against women. So if you include information on the women's issue, the algorithm will still discriminate. Okay? And then if you drop both the information on gender and on the women's issues, there's no longer will be an equal treatment. Which in the case of this example, you might say, well, it's fine if the office doesn't take into account either gender or positions in the women's issue. But if you think about this example, this type of situation more generally, you wouldn't want to always not take into account any information that correlates with the protected attribute, because some of those variables that correlate with the protected characteristic might be relevant to the decision. It might be information that is pertinent to whatever decision is being made. Okay, so if it's information on how qualified people are for a certain job, on the flight risk of someone who is applying for a role, say. Okay, so then, or someone who is being considered for bail, then you want to just not take into account any of that information. So what else can be done? So I'm going to talk a little bit about that toward the end of the presentation. So let me just show you how the data from this example looks like. Again, this is all synthetic data, okay? Hypothetical data. So this is the distribution. These are the density showing the distribution of letter ratings for letters written by women, and that's the black density. And letters written by men, that's the blue density. Okay? So you see that in general, letters written by men receive on average higher ratings than letters written by women. The vertical red line indicates the threshold for making the decision. So letters with ratings above 6 get responses. So with this parameterization used to generate the synthetic data, then the gender gap in ratings is of 2 points along a 1-10 scale, and that results on a woman receiving a response with 23% chance, and a man receiving a response with 87% probability chance. Okay? Okay. So now, in order to show you what happens, what rules are generated by the algorithm, I decided to just show you what happens when you estimate a single decision tree on this data. And so the reason why I chose a tree-based model, a single tree model, is because it's very easy to visualize the structure of the model. It's very easy to visualize the set of rules that are being used to make the final decision. But what I'm saying applies more generally, not just to single trees, but to multiple trees, to standard linear regression models, to any type of supervised learning algorithm, like all of what I'm saying will apply similarly. So I just chose this for kind of exposition purposes. So I imagine that a lot of you already have some training in terms of how it is that you estimate these sort of trees and kind of how you interpret them. But kind of in very, kind of just let me briefly introduce it such that you're able to sort of follow this part of the presentation. So the idea is that we estimate a tree by finding, so what we want to, remember what the goal is. Okay? So we want to come up with a set of decisions, of decision rules, that will lead to decisions that are consistent with decisions made in the past. What does it mean decisions are consistent with those made in the past? It means that the relationship between characteristics of cases and decisions being made, the shape of that relationship, is similar in the old data as in the new data. Okay? We want the relationship between our predictors and the decision to be similar in the old data as for the future decisions that we want to make. Okay? So when this algorithm is being estimated, the way the predictions are generated is that you look at people in the training data set, okay, who are similar in terms of the values of the predictor, okay, and you found which one was the most common recommendation that was made for people with those characteristics. Okay? So how is it that the algorithm is actually estimated? But it's estimated by repeatedly or recursively partitioning the data. Okay, so first you find, so you say, well, was there some predictor in the training data that was that is highly correlated with whatever decisions were made in the past? If there is one predictor in the data that predicts what was done before, then what's going to happen is that it should be possible for you to partition the data along values taken by that predictor, such that when you look at heterogeneity, that is variation in the outcome, within the subpartitions that you create by partitioning the data along that predictor, then after the partitioning happens, within the partitions there should be less variation, less heterogeneity in the area, in the data, than in the original partition. Okay, so consider the example, for instance, of a situation where the only predictor in your data was gender, okay, the gender of the letter writer, and so the outcome was still what decision was made. Okay, suppose that gender was not predictive at all of whether people received a response or not. If gender was the only predictor in your data set, then what the algorithm is going to do is the algorithm is not going to use gender, okay, because the algorithm is going to realize that partitioning the data based on gender serves no purpose. So the prediction that an algorithm is going to generate for that data set is for every case it's going to assign the same predicted probability, which is the proportion of cases that received a response in the past. Okay, so if in the past 50% of letters received a response, then it will just predict 50% chance for every case. If gender was the only predictor and it was not correlated with the chance of receiving a response. Okay? Now, if the algorithm sees that gender did matter, say that most women did not receive responses and most men did receive a response, then the algorithm is going to partition the data based on gender, and then within men and within women, you're going to, among men and among women, you're going to see that there is afterwards much more agreement in terms of whatever decision was made. Most women did receive a response. It means that there is less variation in the outcome among women than originally there was among both men and women. Okay? So that's sort of the logic behind sort of tree growing processes. If you have a second predictor, okay, where you find that after partitioning the data, among women there was something else that correlated with whether they received a response or not. Suppose sharing the same party identification with the legislator. Suppose that after partitioning based on gender, you see that among women there was still some remaining heterogeneity in terms of how they were treated. You can go and see, is that variation correlated with something, with some other attribute of the writers? So if you see that sharing the same party ID mattered, then the algorithm, if it mattered a lot, if the decrease in heterogeneity is large enough after you partition based on party ID, then the algorithm is going to further partition the data among women and so forth. So that's kind of the criteria that it's going to use. The result is that you end up with sort of with sets of rules that tell you for different combinations of characteristics of your observations what it is that should be done in terms of what decisions should be made. Okay? Why is it that the algorithm prescribes certain decisions for certain types of individuals? Because those were the most common decisions that were most commonly made for individuals of that type in decisions made in the past. Okay? Okay, so for those of you who already know about trees, all of this might sound straightforward, but otherwise I feel as if it will help sort of make sense of what I'm showing you here. So what happens when you just estimate it? And what I want to say is that these single trees are nice in the sense that it's very easy when you grow a very simple tree with just a few branches, okay? With just a few splits, okay? So these are very sort of simple tree structures. When you grow a simple tree structure, then the model is easy to visualize. Now, I will clarify that these tend to be models that don't fit the outcome variable very well. There are algorithms that typically can do much better in terms of replicating previous decisions, in terms of goodness of fit. So if you estimate multiple tree models or use other types of machine learning algorithms, you will easily find algorithms that perform better than this. So I chose this only for exposition purposes. Okay, so if you grow a single tree on the synthetic data I described before, then the first thing that the algorithm does is that it zeroes in on gender, because it realizes that gender was highly correlated with whether people received or not a response in the past. Okay? Then among men, it further splits the data based on sharing the party identification with the legislator. And then among men who share the party identification with the legislator, it further splits the data based on position on the women's issue. So men who share the same party ID and who are not supportive of the policy on the women's issue, those are the ones who receive the highest rating and the ones who are most likely to receive a response. Then women who don't share the same party ID with the legislator are the ones who are least likely to receive a response because they are the ones who receive the lowest rating. Okay? So the gender gap in ratings is about 2.3. And these are predictions made out of sample, meaning made for training observations that were not used in estimating the tree. Okay? So the gender gap in ratings is 2.3, the chance that a woman receives a response is 0%, and the chance that a man receives a response is 100%. So you see that this doesn't perfectly fit the training data, because otherwise you would see a gap in ratings similar to the ones that I showed you before, kind of for the ones that I used in generating the synthetic data. And then the chances that women receive a response and that the man receives a response also deviate a little bit from the ones that I also used in generating the data. Okay? But and then something else I calculated for this implementation of the algorithm is the mean square error, which is the average square difference between the predictions that are made by this algorithm and the actual decisions that were made for that portion of the training data that was not used, again, in estimating the tree. So 1.11, it doesn't really mean anything. So the mean square error is not meaningful in itself, but it's going to help us compare these results with results that you find when you start changing the procedure by discarding or not paying attention to certain predictors, okay, or by changing the predictors that you use. So now suppose that you just drop gender. You say, okay, I'm not going to take gender into account. I'm going to take into account positions on issues 1 through 5 and whether the letter writer shared parity with the legislator. And then let's see what happens. Then when you do that, then the algorithm right away finds that variable that was highly correlated with gender, okay? And kind of uses it as a proxy for gender. Okay, so it first splits the data based on positions on the women's issue. Okay, so people who have, for whom this condition holds, position on opinion 5 lower than 0.44. Okay, that low support for the policy on the women's issue. Those end up going toward the right hand of the tree. Remember, a tree structure is analogous to the structure of a flowchart. So it tells you how to apply the rules in the tree from top to bottom, such that you end up making predictions for the observations reaching the final node, consistent with those shown in the final node here. So each final node gives you the predicted rating for letters reaching that node, and also the proportion of letters that ended up in that node, in that synthetic data. So who are the people who are least supportive of the policy on the women's issue? Men. So men end up being more likely to go toward the right hand of the tree, despite the fact that you're not explicitly using gender. When you do that, the gender gap decreases, okay? Because positions on the women's issue are not perfectly correlated with gender. Okay? The chance that a woman receives a response increases, and the chance that a man receives a response decreases. But the mean square error increases. That's an important thing for you to know. So, and this will happen in general. Whenever you take steps, you do things to try to adjust for unequal treatment in past decisions, then your model will do increasingly worse in terms of fitting those past decisions. And that makes total sense. If the past decisions involve discrimination, and you take steps to avoid discriminating in the future, then the future then decisions that avoid, that try to sort of not involve that sort of bias, then will fit the past decisions worse. Okay? So you're going to see that as we keep making changes to sort of get rid of the bias, then the mean square error will continue to increase. So here we are doing, it's another situation where we both exclude gender, okay, and we exclude positions on the women's issue. So now, of course, neither of these variables is being used. The tree structure changes entirely. I would say, when it comes to the tree structure, I use it for visualization purposes, but it's also not something that you should pay a lot of attention to, because for single trees, small changes in the data can lead to big changes in the tree structure, changes in kind of what observations are included, what predictors are included. So this tree structure in itself is not very meaningful. The only thing that I should say notice is that we are not using gender, and we are not using positions on the women's issue. Okay? So the gender gap in ratings is now 0, because we're not using anything that correlates with gender in making our decision, so it's not surprising. And the chance that women receive a response is similar to the chance that a man receives a response, which is 77%. You might say, well, that's great, we got rid of the bias. But in this case, the cost of having done so is not very obvious. Okay? But in other settings, you could easily see how that can be problematic, because you get rid of the bias, but sort of by discarding information. Okay? You discarded information on all predictors. In this case, there was a single predictor, but more generally, we need to discard information on all predictors that correlate with the protected attribute, which is something that you probably wouldn't want to do in a lot of situations. Okay? But you see that mean square error increased even more, because you are fitting the past decisions even worse. So what are solutions to this? What else can be done? So one thing that is you might say, well, but all of these things are super obvious. Why do we even need to kind of discuss this? Well, this is super obvious. Okay, that excluding gender but including things correlated with the protected characteristic would still lead to unequal treatment of certain groups. But that's what the law prescribes in a lot of cases. Okay? What organizations and companies are being told is just don't look at this protected information. But you can consider all other information on the cases. But you see how that's a very naive solution. You see it here. And sometimes, and for you who are used to working with data, this might be obvious. Okay? But for people who sometimes work in these organizations, they are not aware of how just simply not looking at the protected characteristic might not be enough. Okay? So that's why we have this debate on the sort of ban-the-box sort of policies that prevents employees from, say, getting access to people's criminal history. It may happen that they don't look at that, but they take a look at other information that correlates with say, a person's criminal history. So in the end, you end up, or it might happen that the employer doesn't have access to that, so on purpose looks for information that can approximate that. Okay? This could happen with race too. Okay? People don't look at race, but they might take into account all other information about people's behavior that is informative or predictive of the person's race. Okay? So again, that's why we need to talk about it, because it might be very obvious to us, but either there is not enough awareness in the public, or people are aware of it and sort of get around the legal restriction by sort of looking for proxies. Okay, so it's definitely a problem. Okay, but then we need also, the thing that I feel hasn't been discussed enough, especially among the general public, is kind of, well, what else could we do if we don't use that naive solution, but then just we cannot drop everything that correlates with the protected attribute? Well, computer scientists, they have been thinking a lot about this, okay? Because that, of course, is a huge problem for, these issues are a big problem for the industry, who's worried about getting sued for the treatment of customers and so on, okay? People who apply for jobs and so on. So computer scientists have been writing lots of papers recently discussing kind of solutions to this problem. So I'm going to talk about some of these solutions, and I'm going to tell you briefly about one that I personally like, among those that have been proposed, and I'm going to tell you a little bit of kind of how it can be implemented, because sometimes when you think about things abstractly, it sounds as if things are kind of hard to implement, but actually some of these prescriptions are kind of not so difficult to implement. Right? So I wanted to illustrate that using the same synthetic example as before. Okay, so one solution would involve, say, modifying the algorithm itself. Okay, say, for example, you could, when you write down the algorithm, so instead of just trying to fit past decisions as good as possible, Okay? You also can introduce a restriction such that you also want to say either minimize disparate impact or a restriction that tells you that disparate impact shouldn't be larger than a certain amount. Okay? So you can sort of modify your estimation procedure such that you take into account disparate impact. Okay? Say when you do that, you can ensure that groups of individuals that are similar in terms of certain characteristics, okay, receive similar outcomes. You could say, if you think that when it comes to training, okay, for a certain job, people who have similar training should be treated similar in terms of chance of getting the job, then you would want to ensure that people who agree on all of that also have agreement in terms of how they are treated. You don't want them to be treated unequally based on something else. Okay? So that's thing that you could do, or you could, and that's C, you could try to ensure that no sizable group is sort of systematically at a disadvantage. It's treated systematically different. And there the group could be explicitly defined by a protected characteristic, or it could be defined in some sort of latent manner. You could measure it using some sort of unsupervised approach to try to see whether there are latent classes of groups of people who they have certain characteristics and systematically are treated at a disadvantage. There, it's much trickier to say whether that's fair or unfair, because it could happen that the groups are defined over some attribute that is not protected and is pertinent to the decision. Okay? So again, whether all of this is practical, useful, relevant, that will depend on the context. Okay. Okay. But I don't like this type of approach because it's algorithm specific. Okay. So you need to modify the algorithm. So for each algorithm that you want to try out, you will need to modify the procedure to try to minimize disparate impact. Okay? Also, algorithms may be proprietary. You might not have access to the source code, or you might not be allowed to modify it. Okay? And also what might happen is that algorithms can be very complex, okay, in the sense that you might not be able to anticipate beforehand what set of rules are going to be developed by the algorithm. So you might modify your algorithm, and you might not have full control of what the rules are being generated and where the rules won't lead to disparate treatment, or you might eliminate a sort of bias and generate some other sort of bias. Okay. Okay. So the type of approach that I like, that I've been looking at the most so far, involves kind of modifying the training data itself. And so here I'm going back to the notation used by Feldman and co-authors. We talk about some of the issues in the paper. So remember, D is the data set, X is information on the protected characteristic, Y are other predictors in the data set, and C are the decisions that were made in the past. So one thing that you could do is you could modify the original classification. You could say, okay, so who are the people who were treated unfairly? Okay, so who are, say, the people from minority groups who had the training and didn't get the job? Okay, so or the people who didn't have a flight risk who were not granted bail. Okay, so you could say, okay, those people that the classification is going to be modified. We're no longer going to code them as not having been treated favorably to having unfavorably to having been treated fairly. Okay, and you could do that also automatically. Okay, so you could do that using some sort of by writing down some sort of optimization problem, and you could impose a restriction such that you don't make more than X number of modifications, more than N number of modifications. I don't want to use the same letter. Okay. So something else that you could do is you could weight training observations such that those who are treated fairly receive higher weights than those that were treated unfairly. You could weight the predictive items, such as those that are more correlated with the protected characteristic receive lower weights, and the choice of the weights can be part of the optimization problem. Okay, so you could, rather than setting those weights arbitrarily, you can estimate them as part of your estimating procedure, like also writing some sort of optimization problem. But the approach that I really like, that is kind of, it is based on this observation that I discussed before, that when there is disparate impact, okay, then the protected attribute tends to leak onto other predictors. Then if you can get rid of the correlation between the other predictors and the protected attribute, then that leakage will no longer occur and disparate impact will no longer happen. So the really nice thing about this last procedure is that you could implement it before implementing the algorithm. So it involves sort of pre-processing the data before you implement the algorithm. Okay?
I know some students have a class at 3,
okay.
so I'd like to just like Is it okay if people like have a question but you need to go?
So do you have any questions so far that you would like to ask? So far. Feel free to ask questions, to interrupt, whatever, and I will. Okay, so then I will just continue because we have. Okay, sure. So again, you could write down optimization problems that you could use to implement this sort of all of these different approaches. Again, I like this option D because it does not require looking at C. See, if you want to modify the predictive items such that they are not predictive of the protected attribute, then you don't need to look at past decisions at all. You don't look at C. You only look at X and Y, which is kind of, that's nice. And you can also do that before implementing the algorithm, just reprocess the data. So I find it very convenient. So I will show you now very briefly kind of how it is that you could do this. Suppose that you just want to, and this is what I'm going to be doing here. I'm not solving an optimization problem. I'm just going to show you how an easy approach that you can use to sort of to keep all the information contained in the predictive items, except the part that correlates with the protected attribute. Okay? So I'm going to show you a simple procedure that you could follow to implement that. So I'm going to show you how that works for the protected characteristic network. We have only 2 minutes, so I will try to do it fast. Okay? So first, what you do is you calculate quantile functions within classes defined by the protected attribute. So the protected attribute says gender. The classes would be men and women. Okay? So within each group, you calculate a quantile function that gives you values of the predictor within the class for every quantile. Okay? So for example, remember that when I generated statistic data, women were more supportive of the policy on women's issues than men were. So if you look at the lower end of the distribution for women, okay, say you look at the first quartile, okay, the 0.25 quantile, it should be larger for women than for men, meaning women on the lower end of the distribution should be more supportive of the policy than men on the lower end of the distribution. That's indeed what you find. So women on the first quartile of the distribution on that issue display a position on the issue of 0.5. Remember, positions on that issue range from 0 to 1. Okay? So 0.5 is indifferent. And but men had a position lower than 0.13. Okay? So they tend to be non-supportive, men in the same position on the distribution. So then the next thing that you do is you calculate a median quantile function, meaning you take the median over quantile functions across the classes. Okay? So what would that median quantile function tell you about the first quartile? Okay. So what it would do is it would take the first quartile among women, the first quartile among men, and calculate the median. Okay? And since there are only 2 classes, that's the average of 0.5 and 0.125, okay, which is about 0.3. So that would be the median quantile, okay, for the first quartile, okay, generated by the median quantile function, okay, for the synthetic data that I showed you before. Okay. Then for each observation, what you want to do is you want to create a modified version of the predictor that was correlated with the protected attribute. So suppose that Y was the original predictor. Okay? Here we're looking only at position on the woman's issue. And Y bar is a modified predictor. So Y bar, you generate it using that median quantile function. Okay? And how do you do it? You want that that modified predictor to be rank preserving. So what does that mean? It means that if you take women and you sort them from lower value to highest value based on values taken by the modified predictor, you want the order of women to be similar to the order that you would see if you use the original measure of the predictor. Okay? To ensure that is the case, then what you do is you look at, well, within what quantile was this person according to the original distribution of the predictor. Then you look for the same quantile for the value of the predictor corresponding to that same quantile according to the median quantile function. So for example, a woman who had a position on the women's issue of 0.5, okay, along the original version of the predictor, will now be given a position of 0.3, okay, by the median quantile function. So opinion 5 alt, that's the label that I used for the modified version of opinion 5. So you see that the position of that woman is adjusted from 0.5 to 0.3. It's adjusted downwards. And the position of the man, who was in the same quantile, okay, is now adjusted from 0.125 to 0.3. Okay, so positions for men are going to generally be adjusted upwards. From women, they're going to be adjusted downwards. Okay, And again, as I said before, by construction, this method is kind of rank preserving. So you eliminate the correlation that's between gender and the predictor, okay? But within classes, you preserve the order. So we are preserving information that contained in that predictor that is not correlated with the protected characteristic, but that might be relevant for your decision. Okay. So this is what happened in the case of the synthetic data I showed you before. These are the distributions of the positions for the support for the policy on the women's issue among women. That's the black curve, and among men in the original, according to the original version of the predictor. So men were generally less supportive than women. So after you make the adjustment, following the procedure that I described before, then there are no longer differences between positions of men and women on average, although there's still a difference in the dispersion here. Meaning, and this happens because you have more outliers among women than among men along the original measure. And so today I had an interesting discussion with someone about how when this happens, this can still lead to some bias. Even though you perform that adjustment, you might end up, some bias may remain in terms of how different groups are treated. And I think this is something I need to explore more because you're going to see that some bias remains after doing that adjustment. And I think that the reason why that happens is because you have more women toward the end of these distributions, especially you have more women who had very large values along the scale. So even if you adjust downwards, the downward adjustment that you do for women might end up being smaller than the downward adjustment that you do for most men, meaning that the adjusted measure could still, to some extent, tell you for some people like whether they are men or women, just because they are still in the extremes of the distribution. So the idea is that if you look at the adjusted distribution, if you know that somebody is kind of on the extremes of the distribution, that tells you that that person is likely to be a woman. Okay? So that's something I still need to think a little bit about and think about, well, maybe one thing that you could do is to do some processing or add some additional step where you adjust for the existence of outliers before doing the adjustment using the quantile function. I still need to think about that. But what happens if you just implement the algorithm on the same synthetic data I created before? So you exclude gender, but you include the modified version of the women's issue. So now that measure so notice here that if you look at the correlation between the original measure and gender, the correlation was positive and about 0.5. After the adjustment, the correlation is close to 0. Okay? So after you eliminate the correlation, the positions of the issue are still used on the adjusted issue. And that makes sense because when I generated the synthetic ratings, I did so such that positions on the issue mattered beyond gender. So men with favorable position on the women's issue were also receiving lower level ratings. Okay? So that information is still used in estimating the tree. Now the gender gap in ratings is smaller than when you included say you exclude gender, but include the original version of the women's issue. Okay? Now when you include gender and the modified version, the gap is slightly smaller, but there's still some gap. That's what I was saying before. It didn't entirely disappear. The chance that women receive a response is 32, that a non receive a response is 59, and the mean square error is 1.9, which is still larger. Remember that the original mean square error was 1.11, so you increase the mean square error. So I believe that the main takeaway of the presentation so far, and I think because this is something that if you look at the machine learning literature, statistics literature, when we fit models, we want to achieve greater goodness of fit, the best possible goodness of fit out of sample. That's always the goal. Okay? But then what we realize when we start thinking about this problem is that if we care about equal treatment of different groups, then that cannot be the only goal. Okay? Because if you only care about goodness of fit, then you won't be able to adjust for the unfavorable treatment of individuals when previous decisions were made. So getting rid of the bias, forgetting the bias, requires doing a worse job in terms of fitting past decisions. That's it. Right? So you might write down some optimization problems such that you don't go as far as possible when it comes to reducing the bias, but you still admit some decrease in fitness. Okay? So there is this kind of trade-off between both things, and I feel as if that is something that we should spend more time discussing, because so far the only goal of all estimation procedures is usually just fitting the outcome variable as good as possible. Okay, so there are, in terms of social science examples, so far, I've been kind of mostly sort of writing all the problems, like trying to read social media and the news, trying to come up with kind of interesting examples of all of these, and then working a little bit with these synthetic examples. And synthetic simple examples are useful because they help you see the limits of some of the proposed solutions. Okay? So you can, with data that is kind of very simple, you can easily see where the problems emerge. Where sometimes with very complex data sets, it might be hard to figure out what exactly is going on. Okay? But I would like to now also start looking at real data, and I think that the real data set that I will use for this paper will come from some audit study, because there are so many audit studies in political science that have been conducted in recent years to look at kind of bureaucratic responsiveness and how it varies depending on the type of person who's either requiring information from the bureaucracy or submitting applications through the bureaucracy. Okay? So a lot of experiments, audit experiments have been conducted, and we have so many replication packages that have the type of data that I would need for an application like this one. So I think that I'm going to be working on that, but there are examples from all over the social sciences that also could be used that I might work on in the future depending on kind of access to data and so on. So that's it. Here's just a summary of some of the things that I said. So just dropping indicators of protected characteristics is not enough. Dropping everything that correlates with a particular attribute, that's not desirable. There are better solutions. We should look at the computer science literature because they have been proposing like really clever approaches to start dealing with this sort of problem. And this is kind of dispiriting and depressing, because to say this at the end of the talk is kind of, why did I listen to all of this? But everything I said requires having an access to a measure of the protected attribute. If you don't have information on X, you cannot perform the type of adjustment that I was talking about. Okay? You cannot perform any of the adjustments that I talked about. Okay? And many times, decision makers are forbidden from looking at a certain protected attribute. So they might want to perform this sort of adjustment, but they might not be able to do so. They might be able to sort of perform some sort of data mining to sort of infer what the protected attribute is, given that they don't see it. But would that be ethical? Probably not. Like if you're not allowed to say consider a person's gender or race, you don't want to infer it in order to later apply these sort of procedures. But if you don't see it directly, then the problem with not seeing the attribute directly is that you cannot implement any of these approaches, and also that the entire process becomes very little, there's no transparency. It's that you could actually have a decision maker looking for a predictor that correlates with whatever they are not allowed to see, using it and then pretending that they didn't know. Okay? So again, so there's also a lot to discuss about should decision makers have or not have access to information on protected attributes? Because there's a cost associated with not letting them see. Okay? You cannot implement any of this, and also what I was saying, like lack of transparency. Okay, so that's it.